Hello class, ready to look at lesson 2.9, which is titled Parts of Speech Using Operations Correctly. So one of the purposes you'll find in this video is being to understand, what when we do an operation, what are the things that we're performing the operation on, and then also how to think about the operations correctly, right? With the explore problem, we're filling in this table by filling in the missing boxes. So the first one's done for us. So you can see, let me grab this. All right, so we can see this first row. We have radical 17. The object is 17, and this in the operation is the square root, right? So if we look at the second row here, part B, we're looking at 4 and 2/5, and the objects here are 4 and 2/5, and the operation between them, right? We can think of 4 and 2/5 as 4 plus 2/5, right? 4 and 2/5 more. So the operation in between those, we can think of that as addition. So then part C, we have 8/9, right? So my objects are, we have 8 and 9, and the operation in between those would be division, right? The next item, we have absolute value of -10, right? We're already told the operation is absolute value. So my object is what am I doing the absolute value to? And that is -10. Right? So then part E, we're told the operation is square, and what's the object that we're squaring? The object that we're squaring is -8. Right? Part F, again, something similar, except we don't have the parentheses around the -8. So what we're squaring, the object we're squaring, is only the 8. Right? So this is hard sometimes for students to understand that these two things are different. And what's different is what the base is, right? When I have -8 in parentheses squared, I'm putting the parentheses around -8 because I want to explicitly show that the -8 is the base, right? So this is equal to -8 times -8, so we get positive 64. Without the parentheses, I have -8 squared. Then the square, the exponent 2, is being applying only to the 8, directly to the 8. So this can be thought of as the opposite, right, of 8 squared. So -1 times 8 squared. Right, that's how this is read, the opposite of 8 squared. So 8 squared is 64, so we want the opposite of 64, which is -64. Right? Just like if I write down -5, right? This is the opposite of 5. So this is -1 times 5, right? To find the opposite of something, the added fit inverse, we can just multiply by -1, right? So these two things are different, and it's because what the base is. Right? So then in part G, we have the expression 2 times x plus y, and we're told the operation is multiplication. So the objects would be 2 and x plus y. Right, so those are the two objects that I'm multiplying together. Right. Part H, I have a plus b all over 2. I'm told my objects are a and b. So what operation is going on between a and b? Right. So we're just looking at this part. Right. So what's going on between a and b is that we're adding them. Right. So this would be addition here. And then part I, we're given the same expression, and the objects are different though. We're given a plus b as one object and 2 as another object. So what's going on between those are division, right? Then part J, I have a over 2 plus b over 2. And I'm asked, these are my two objects, a over 2 and b over 2. So what's going on between them, right, is addition. And then lastly, part K, We're given the same expression. We're told the operation is division. So what's going on between them, or what's the objects that are being divided? Well, that's A and 2, right? A and 2, and then B and 2. Right, so we actually have two things being divided, right? So we have like two sets of objects. So A and 2 and B and 2. Right? So hopefully that got you thinking about what types of operations are going on between the different objects. So in the Discover, this reading is talking about how using parentheses and different spots is kind of related to putting commas in different spots in terms of meaning, right? So for example, here we're told to look at these two sentences. So the first one, I like cooking my family and my dog, right? How that is interpreted is that someone cooks their family and their dog, right? Which is probably not the meaning, hopefully not. So the second sentence with commas is a list, right? So it's saying I like cooking, I like my family, and I like my dog, right? So these commas have a distinct meaning, right? And typically we might try to like autocorrect, like if we saw the top sentence, we'd probably kind of autocorrect that on our own, but it wouldn't be written in the correct way, right? So in mathematics, I think it's even more important to have correct grammar with mathematics, if you will, because you can't always like kind of autocorrect the mathematics expression like you could the sentence, maybe, like given the context. So it's not nearly as easy, I don't think, for everyone, right? So it's extra important to be careful with the mathematics, right, and what operations are going on with the operation. So then the next part in the book, right, we have some more reading that I encourage you to read over on your own. So I'm just pointing out some of the highlights, right? So like here in this box, they're talking about how like without parentheses and with parentheses, these two expressions mean totally different things, right? The first one means that I'm taking -8 minus 8, right? Where the bottom operation here is multiplication, right? When I have two things side by side in parentheses, that means I'm multiplying, so -8 times -8, right? So those mean completely different things, right? And sometimes also parentheses aren't so important, right? So like if I have I don't know, like 4 plus -2, right? If I had 4 plus -2 in parentheses, right? These mean the same thing, right? A lot of times when we look at negative numbers, some people like to put parentheses around it, and it's just to emphasize that this sign goes with the 2, right? That's perfectly fine. So sometimes they don't necessarily have a distinct meaning, but in this case they clearly do, because without with the negative with the -8 in parentheses, this does have a important meaning, because the parentheses are telling us that we multiply, right? So it's holding like an operation, where here these parentheses are not providing any detail into the operation, right? It's just more of a preference, really, right? So some things to think about. So then the next item here that we can read over is talking about the distributive property, right? And how having a plus sign here, right, really means I have two objects or two terms inside the parentheses, so I do need to distribute the 3 to everything, right? Where in this problem down here, I'm taking 2x times 9 times 3. So this, you should be able to recognize that this is not distributive property, right? These are just 3 things multiplied times each other, right? So there should be no distribution, right? The only time we distribute is if I have more than one term inside the parentheses, and 2x times 9, this is all one term, right? Remember that terms are separated by addition and or subtraction, right? So I could have like A, B, C, D, E, F, G, right? Maybe I'll put like 24 up front of here, right? This is all one term still, right? So this is one term. And you could keep adding, as many things as you'd like, right? We can keep multiplying by, 100 different things, and we still only have one term, right? What dictates a term is if I have an addition sign or a minus sign, right? So, which is just adding the opposite, right? So that's what separates and distinguishes terms from one another. Right. So then here we're looking at we went to half a recipe that requires 4.5 cups of flour, and we're looking at is this method valid? And it is by the distributive property, right? So so when you divide by 2, that's the same thing as multiplying by half, right? So and also we looked at last time with a mixed number. I think it was 4 2/5 that so 4.5 is the same thing as 4 plus a half, right? And before, like I said, I think we had 4 2/5. So 4 2/5 equals 4 plus 2/5. Right. So this this idea can be helpful when working with mixed numbers, and especially I like to show like when we're multiplying something by a mixed number. I think this can be an easier way to do that, and that's what they're doing here, right? So I'm rewriting this as a half times 4.5, but then they're separating the 4.5 here by taking 4 plus a half. So then now I need to distribute the half to each term, right? So I have the term of 4 and the term of a half, right? So 1/2 times 4 plus 1/2 times a half gives me 2 plus a fourth, right? Or I can just write that as a mixed number, right? So if I can take a mixed number and pull it apart, I could do the opposite, right? So if I have 2 plus a fourth, that's simply just 2 1/4, right? So we would need 2 1/4 cups of flour, and in this case, if we're halving the recipe, right? All right, good. And then we're just showing this for a general case, what that looks like, right? So if I have a plus b over 2, that's the same thing as a over 2 plus b over 2, right? And again, maybe going this way might seem a little odd, but if we go in this fashion, right, how we add fractions together, we keep the denominator the same, right, and then we add what's in the numerators together. We're counting, how many of those objects that we have. So if that's true, then the reverse would also have to be true, right? So if two things are equal in mathematics, right, they have to be able to go both ways, right? And then here, it's just also proving this through the distributive property, right? So similar to what we did, just looking at it in general terms, right? So instead of dividing, we're writing it as multiplying by half, and then we have to distribute the half through, and then the reducing at the end, right? So this is, in essence, a proof to showing that these two things are equal to one another, right? All right. So next, you're given an example, and you're asked to simplify, and then we're given a solution, right? And if when you're looking through this in the e-text, I encourage you can click on this link here. So this link here, right? And you can watch the video. And the author's like working through this example, right? So that might be helpful to follow along if you aren't so much of a you don't learn well by reading. Maybe you learn better by reading and have audio visual to support your learning, right? So for example, I'm very much a visual auditory learner. So that's really helpful for me, right? So if you're like me, feel free to check out this video also as you're going through. All right, so I can talk about this a little bit. So it's to simplify 4x plus 1 over 4, right? So here, notice what the author did is we split up the fractions, right? So using that similar idea that we had before, where if if I have 4x over 4 plus 1/4, then how I would add these up, right? I keep the denominator 4, and then I'm going to add the numerators together. So this would be 4x plus 1, right? So what we're doing is, instead of adding them together like this, we're starting with this expression, and I want to rewrite it in this way, right? And this can be helpful for us when we're trying to reduce down things, right? Simplify things. So that's what we did, and then now we can simplify this first fraction, right? 4x over 4x, or 4x over 4, excuse me. So we can divide top and bottom by 4, right? Which means I have 1 left in each spot. So that leaves me with just x, right? This term, and then 1/4 I can't do anything with, right? So I'm left with x plus 1/4, right? And then this process is important because so many students, when you're asked to simplify this, they get in the habit of like crossing things out, and they just want to cross these out and make this x plus 1, right? But notice x plus 1 is not equal to x plus 1/4, right? And the problem is you're not dividing this term by 4. You're only dividing the first term by 4. So the way this is written, we're dividing every term by 4. So it's good you're crossing these 4's out. You're recognizing that I can divide 4x by 4, but you're leaving this guy out, right? You're forgetting to divide him by 4, right? So it's more useful at times to rewrite the fractions in this fashion, right? And then simplify, so that way you don't forget that, right? Or another way that might be helpful, and let me work this problem in another way. So we have 7x plus 7 over 7 for part 2a, right? So kind of another trick you can do is you have to think about it like this. These are two separate fractions, right? So then I need to reduce each part. So 7x over 7, right, is just 1x. And 7 over 7 is just 1, right? So I would have 1x plus 1, right? So you can kind of, if you like to maybe do it a little more mentally, you could do it this way, right? But if that doesn't work for you, or that you'd rather write it out, then I would do that, right? So let's try it by writing it out, right? So 7x plus 7 over 7, right? We can split this up by doing the first term over 7 plus the next term over 7, right? So I have 7x over 7 plus 7 over 7. And then we can simplify each part, right? So 7x divided by 7 is simply just x, right? And 7 divided by 7 is simply 1, right? So I'm left with x plus 1, right? Which is the same thing as 1x plus 1, right? But again, typically we don't write this coefficient, right? Because 1 times anything is just itself, so it's technically not simplified if you write that down, right? We're trying to be as precise as possible, right? So part B, we have x minus 7 all over 7. So again, we can split this up in a similar way. So you take your first term, x over 7, and then plus your next term, which is negative 7 over 7. So then this gives me, so x over 7 I can't simplify, right? So we just get x over 7. And then negative 7 over 7, I can simplify that to be negative 1, right? And then if you'd like, we could rewrite this as x over 7 minus 1, right? So plus and negative is the same thing as just subtraction, right? So in other words, if I have a minus b, that's the same thing as a plus negative b. Oops. Sorry, that b does not look good. Right. All right. So then part C, right? It's important to realize this is like the opposite of this fraction, right? So you may want to write this as negative 1, and then maybe a parenthesis times, and then split these up so we could do x over 7 minus 7 over 7. Right. So then if we distribute the negative 1 through, This leaves me with negative x over 7 plus 7 over 7, right? So it just changes the sign of these. And then I can simplify, so we'd have negative x over 7. I can't do anything with that. And 7 over 7 is just 1, right? So we get negative x over 7 plus 1, right? Another way you could do these if you wanted, so let me get some different color here. So like I'll just do the first one this new way. So if I have 7x plus 7 over 7, right? We can think about this as I have two objects, 7x plus 7 and 7, and the operation between them is division, right? So in other words, I have 7x plus 7 divided by 7. I apologize, I'm getting a lot of emails coming in, so let me just go ahead and just get rid of that. All right, so hopefully they won't be distracting. Sorry about that. So 7x plus 7 divided by 7, right? That's the same thing as multiplying by the reciprocal, right? So in essence, this would be the same thing as if I took 1/7, right, which is the reciprocal of 7, times 7x plus 7, right? And then I can distribute the 1/7 through, and I get x plus 1, right? So I still get the same answer. Just think about it a little different way, and that's fine too, right? It means that these two different ways of thinking about this are equivalent, right? As we looked at one in the last section, right? All right. So next we're looking at, so it says, as we have seen, we can distribute division over a sum, but can we distribute a sum over division, right? So it says when answering questions like this, remember that only deductive reasoning using the general case can prove a statement, right? So we have to use some deductive reasoning skills. And also we have an important reminder here telling us that examples are not enough to prove a statement, but if we can find a counterexample, then that's enough to disprove a claim, right? So in other words, it's typically in mathematics, it's harder to prove that something is true in every case, right? Sometimes, given some context, it's easier to find one oddball, one example that doesn't work for what you're trying to prove. So that's a counterexample, so it disproves it, right? It proves it false, right? So for example, if I wanted to prove that everyone in the U.S. lives in Ohio, right? So every U.S. citizen lives in Ohio, right? So if I was trying to prove this, it would be very easy for me to just to find one person that's a U.S. citizen that doesn't live in Ohio, right? So for example, I could call my friend from college, my roommate from college, who lives in Indiana, and he's a U.S. citizen, and he does not live in Ohio, right? He lives in Indiana. So that'd be a real easy way to prove that, right? So in this case, my counterexample would be Chris, right? My friend, right? Who lives in Indiana. So that's easier to do than to track down every U.S. citizen and see if they live in Ohio, right? So that's kind of a maybe a goofy example, but hopefully that kind of helps make sense for what counterexamples are and how that can be effective, right? So like number 3, right? It says, are the following two expressions equal? 2 over a plus b and 2 over a plus 2 over b, right? And the key here is, are they always equal, right? So certainly I could plug in some values for a and b, and there's most likely some cases that would hold true for both cases, right? So I'm just going to try something easy, right? So let's just say let's let a and b both be 1, right? And see what happens, right? And if I plug in a value for a and b, and it turns out that these two things are equal to one another, then I need to find something else, right? Because that's not a counterexample, right? A counterexample is where we found an example that disproves it, right? Makes it false, right? So we need to find our Chris, right, if you will. So this would be 2 over 1 plus 1, And instead of writing equals here, I'm going to write it equals with a question mark above it. So when we're trying to prove that something is equal to one another, it really bothers me to write equals because we don't know if they're equal, right? We're trying to see if they're equal. So writing a question mark above it just tells our reader that we're questioning their equality, right? We don't know if they're equal, right? So when you write an equal statement in mathematics, we're saying they are equal, like they're definitely equal, no questions asked. But here we do have questions to ask, right? We're trying to figure out if they are equal. So we're just plugging in our values for a and b. So I have 2 over 1 plus 1. Is that equal to 2 over 1 plus 2 over 1? So on the left-hand side, what we end up getting is 2 over 2. And, we're trying to see, is that equal to, it would be 2 plus 2, right? 2 over 1 is 2. So then 2 over 2 is 1, right? And 2 plus 2 is 4. So these are not equal to each other, right? So this is my counterexample. It proves that this is not true all the time, right? It may be true, but not true in general sense. So this isn't something that we could do, when trying to work with expressions. We can't split them up if the a plus b is in the denominator, right? Only if it's in the numerator. Right. So then number 4, we're doing something similar, right? We're trying to see if I have a plus b squared. Does this equal a squared plus b squared? Right? And there are certainly other ways to prove this, but one thing that we can do is use a counterexample, like we were asked. So we need to pick values for a and b, and we want to find where these aren't true, right? Again, I'm going to put a question mark here just to show that we're testing their equality. So in this case, I don't know, let's let a equal 2 and b equal to 4. Right? We'll see what happens here, right? So if I plug these values in, I would have 2 plus 4 all squared, and we're seeing, is that equal to 2 squared plus 4 squared, right? So on the left-hand side, I would get 6 squared. Is this equal to, so 2 squared is 4, and 4 squared is 16, right? And then 6 squared is equal to 36, right? So is 36 equal to, so 4 plus 16 right here is 20, and these are not equal, right? So this is my counterexample. So when a is 2 and b is 4, we prove that this is not true. So this is not true in general sense either, right? In fact, a plus b squared means that we take a plus b and I multiply it times a plus b, right? So here we could FOIL, right? We could multiply these polynomials together, and what you would get is a squared plus 2ab plus b squared. Right, so if you've already seen how to multiply polynomials, which I'm sure you have, at some point in your career, so remember you have to distribute each piece, right? So we take a times a, and then a times b, and then b times a, and then b times b. Right, so you have to take each term in the first polynomial times each term in the second, right? So that's an easy way to prove. Or you can also look at a diagram. So a plus b squared, we can think about it in terms of a square, right? Because the area for a square is s squared, right? So I'm letting a plus b be like my s, where s is your side length, right? So in other words, this side measures a plus b, and this side measures a plus b, right? So what I could do is draw another square side of here where it cuts this into 4s, and I can make this be a and this be b, right? Because this whole side has to equal a plus b, and this whole side has to equal a plus b. So I can make this a and this b, right? So this side, so let me maybe use different colors. So this line segment here measures a, and this line segment measures b, right? So if I put them together, I still get a plus b, right? And the same thing with this side. So with squares, right, we know that opposite sides are parallel, and they also are congruent in length, right? So this would be measure A. This would measure A and A. This would be A still. This is B, B, and A. And then this is A and B. And this is B, B, B. All right, so then I could find the area of each square and then add them up, and that would be equal to the total area, right? So if I have a square that's A times A, this would be an area of A squared, right? This one is A times B, so AB. This square is B times A, so we could write that as BA or AB, right, using the commutative property. And then here, this is a B by B square, so the area of that would be B squared, right? So if I add up all of these areas together, then I will get A squared plus 2AB plus B squared, right? So this might remind you of the box method when multiplying polynomials if you've seen them before, right? So this is a visual way to represent it, but it also gave rise to the box method. Or if maybe you've taken biology and done like I think they're called Punnett squares, where you're crossing two genes and seeing what traits are likely to happen. Then that also reminds me of that as well. All right. So I believe you'll cover we'll cover a section on multiplying polynomials more explicitly, but just to get your mind understanding number 4 a little further, like how we think about it, right? Because one part of this class is trying to get you to think more, as someone successful in mathematics, a mathematician, how we think about things, right? So this book is really meant to be a more natural way to think about and talk about mathematics, right? Instead of being so more traditional sense, right? And the traditional sense is a great way, but I think that way may not be successful for a lot of people. So this book was meant to be a more natural way to think about things and so forth. So I hope this textbook and this course is helping you build a good foundation for taking your next math class, right? All right. So then we have the connect, right, which is the last part before the reflection. So the connect, you can read over this. It's just talking about how we have operations that are inverses of each other, like multiplication and division, squaring and square root, and so forth. And we're given an example where we're folding a piece of paper and putting in an envelope to mail it, right? So if you mail a letter to someone, right, the first thing you do is you fold your letter, right? So it'll fit in the envelope, and then you put it in the envelope, right, number 2, and then you're going to seal the envelope, right? And then the person who receives it, right, they do this backwards, right? They have to first unseal the envelope, right? Use a letter opener or your finger, right, whatnot, and you have to, break the seal of the envelope, and then we have to take the paper out and then unfold the paper to read it, right? So notice we're doing everything in reverse, right? And these actions that we're doing backwards have to accomplish or undo the task, right? So here, seal the envelope, and here we have to unseal the envelope. So that they're opposites of each other, right? Or fold the paper and unfold the paper, right? Those are opposites of each other. And then place the paper in the envelope and take out the paper. Those are also opposites of one another. Excuse me. All right. So the next, I want to look at these two examples. Let me make this text a little bigger. All right. So we're on number 5 on page 220, right? So we're told to evaluate each expression when n equals 5, and they want us to list the operations that we applied to the value of n in the order that they were applied, and then we're going to make a second list of operations that contain the inverse operations, and we're going to do them in reverse order, right? So in the way that someone would open the letter, in a sense, right? All right. So we want n equals 5, right? So we'll plug in n equals 5. So we have 3 times 5 squared minus 2, right? And don't forget we have order of operations, right? So easy way to remember them, we can remember them by the acronym Pemdas, right? So the first thing we need to do in this case would be to square the 5, right? So I'm just going to make a list over here. So the first thing we need to do is square the 5. Right? Or I'll just write just square, right? The first thing we're doing is square. That's the operation. So then by squaring that, what we would get is 3 times 25 minus 2, right? So then the next operation that we'd have to do here is we need to multiply, right? Multiply by 3. So multiply by 3, right? So if we multiply by 3, so 3 times 25 is 75, right? And then we have minus 2. So then the next operation that we need to do is to subtract. We're subtracting 2, right? So 75 minus 2, we get 72, right? So there's the solution that we get, right? That's the value of the expression when n equals 5. And then over here's my list of solving, right? The steps that we took to simplify that. So now we're trying to think of the inverse list, and this will be helpful for us when we look at solving an equation, right? What steps do we do? And essentially when you're solving an equation, we're trying to work backwards, right? So we're trying to find what n is equal to. So we're, in other words, we're the recipient of the letter. We need to open up the letter, right? Do everything in reverse. So the first thing that we would do to solve this, right, would be the opposite of the last step. So the opposite of subtracting 2 would be to add 2, right? So then, so we're going in this way, right? So this is what we do first, and then second, and then third, right? So the second thing that we would do, we need to do the opposite. We need to undo the multiplying by 3, right? So we would divide by 3. And the third thing that we do, we would do the opposite of squaring, which is take the square root. Right? Good. All right, so let's work through the next one. So again, we want n equals 5. So I'll plug in 5 into this. We would have 2 times 5 minus 1 all over 3. Right? So the first thing that we'd want to do following order of operations is work through the parentheses, right? And there's only one operation in parentheses, so what we would end up doing is subtracting 1. So subtract 1, right? So if I subtract 1, then I would have 2 times 4 all over 3, right? So again, following order of operations, the next thing I would do would be to multiply by 2. Multiply by 2. So we would have 2 times 4, which is 8, all over 3. And then the next, the only operation I have left is to divide. Divide by 3. Divide by 3. So when I take 8 divided by 3, what you get is 2 and repeating 6s, right? So 2.66 repeating. Or if you want to round that, approximately 2.67, right? So then again, I want to do this in reverse, right? Operations that are undoing. So I want to go in this way. So this is my first step, my second step, and my third step, right? I want to undo those. So the first thing that we would do if we were solving this is to do the opposite of divide by 3, which is to multiply by 3. The second step, we want to do the opposite of multiplying by 2, so we would divide by 2. And then the third thing we would do, the opposite of subtract from 1, right? Undoing subtracting 1, so we would add 1. Right? So we've accomplished those tasks, right, that we were asked to do. So then with the reflection, right? So we're just wrapping up this lesson. So the important thing is that it's important to understand the role of operators and objects in mathematics, right? And that this knowledge will pay off as you move into the second half of the cycle and learn to solve equations, right? So solving equations. And then, so what did we learn? We learned how to distinguish between an operator and an object, how to determine on which objects an operator is acting, right? And how to recognize when distributive property can be applied, right? So these are all important mathematical skills. All right. Well, that's all for this lesson. So feel free to reach out to me, email me if you have any questions over any. Thanks.